walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking, but there's no time for regrets.
Hi, welcome back to my class in Abstract Algebra. Today we will start with one of the algebraic structures that we will study in Abstract Algebra. And this particular algebraic structure is called group. What is a group? A group consists of a non-empty set and a binary operation defined on that non-empty set. And together, the non-empty set and the binary operation defined on the non-empty set must satisfy three specific properties for the non-empty set together with the binary operation defined on the non-empty set to be called a group. These three properties of a group are, number one, associativity. That is, the elements of the non-empty set must satisfy the associative property under the binary operation defined on that non-empty set. Number two, in the non-empty set, there must exist an identity element such that when any other element of the non-empty set is combined with this identity element using the binary operation, the result is that element, that any other element of the non-empty set. The third property of a group is the existence of inverse elements. That is, every element of the non-empty set must have an inverse. And when the element of the non-empty set and its inverse are combined using the binary operation defined on the non-empty set, the result is the identity element of the set. That is why the second property, the existence of identity element of the non-empty set, is given ahead of the third property for the existence of inverse elements. We now formally define group as an algebraic structure. Let G be a non-empty set. Then G together with the binary operation star in G is called a group if the following are satisfied. G sub 1, A star quantity B star C is equal to quantity A star B star C for every A, B, C elements of G. G sub 2, there exists E element of G such that E star A is equal to A star E is equal to A for every A element of G. And G sub 3, there exists A prime element of G such that A star A prime is equal to A prime star A is equal to E for every A element of G. Now let us analyze the definition of a group. Again, as I said earlier, there are two entities involved in a group. The first is a non-empty set. In this definition, the non-empty set is denoted by capital letter G. And when we say a set is non-empty set, there is at least one element on the non-empty set G. And that means we cannot define or describe a group on an empty set or a null set, that is a set with no elements. The second entity involved in a group is a binary operation. In this definition, the binary operation on G is denoted by this notation, which we read as star. And this binary operation is defined in the non-empty set G. Actually, a binary operation defines a map of sets. It defines a function from the cross product of a set to the set. In symbols, this is how we define a binary operation denoted by star. A binary operation star is a mapping from the cross product of set G with itself to set G. That is, the elements of A cross G are ordered pairs of elements of G. And this ordered pair of elements of G are combined by the binary operation star to produce a single element that is also contained in G. Thus, a binary operation defines a function from G cross G to G. And a group consists of a non-empty set G and a binary operation defined on G, in G. In this definition, because this definition is general, the binary operation star is not specified. But you have taken some examples of binary operation in algebra defined on the set of real numbers. You have the binary operation addition and the binary operation multiplication. Also, in the study of sets, you should have studied that, you should have learned that union of sets and intersection of sets are binary operations on sets. Because these set operations, union and intersection, combines two sets at a time to produce another set. Now, a non-empty set G together with the binary operation star do not constitute a group without satisfying these three properties of a group. And these three properties in the definition are denoted by G1, G2, and G3. The first property, as I said, is the associativity or the associative property. And this associative property must hold true for any three elements of the non-empty set G. And these three elements are denoted by A, B, C, and these are arbitrary elements, which means that they can be any three elements from the non-empty set G. Now, in case if the non-empty set G consists of only one element, then A, B, C will all be equal to that one element of G. And the associative property says that for any three elements of the non-empty set G, A star quantity B star C must be equal to quantity A star B star C. And this associative property must hold true for any three elements that you take from set G. And the second property of group denoted by G2 is the existence of identity element. This property says that there is one element in the non-empty set G such that if you, in the definition, this one element in set G is denoted by small letter e. There exists small letter e element of G such that if you combine this one element with any other element from the non-empty set G, and this any other element of the non-empty set G is denoted by small a. If you combine this with the element E that is containing G using the binary operation star, the result is that element A. And this element E of G is called the identity element of G. And the third property of a group is denoted by G sub 3, and it is the existence of inverse elements of the elements of G. This property says that if you take any element of the non-empty set G, that element has an inverse. In this definition, the inverse is denoted by A prime. And this property tells us that if you combine the element of G, any element of G, with its inverse, using the binary operation star defined in G, the combination of A and its inverse combined by the binary operation star is equal to the identity element E. Now we take some examples of groups and we will verify whether the given non-empty set together with a binary operation defined on the non-empty set is a group. Now for you to check if the given set with the binary operation defined on that set is a binary operation, you have to verify that whether these three properties are satisfied by the elements of the given non-empty set under the binary operation defined on the non-empty set. If at least one of these properties is not satisfied, then the given non-empty set with the binary operation defined on the non-empty set is not a group. If all the properties are satisfied by the elements of the non-empty set with using the binary operation defined on the non-empty set, then you can conclude that the non-empty set together with the binary operation defined on the non-empty set is a group. Our first example of a group is the set of integers under the binary operation addition. And the set of integers is denoted by capital letter Z. The set Z, this is the set of integers under the operation addition, is a group. And we will check if this is true, and to check is to verify if the three properties of a group are satisfied by set Z, the set of integers under the binary operation addition. The set of integers, as you have learned, is divided into three subsets: the set of positive integers, the set of negative integers, and the zero integer. And all these, if you take the union of these three subsets, the union of the set of positive integers and the set of negative integers and the set of zero integer, the result is the set of integers denoted by Z. Now we verify the first property, associative property, we take any three elements from C, and you may denote these three elements, these arbitrary elements from C, using any small letters. And I will use A, small letters A, B, C. We let A, B, C be elements of A, B, C, elements of C. This means that these elements A, B, C are integers. They may be positive integers, negative integers, or zero integer. And we verify the first property, associative property, under addition. We must show that A plus quantity B plus C is equal to quantity A plus B plus C. In the definition of group we had earlier, the binary operation star in the definition is now the binary operation addition, denoted by the symbol plus. So for associative property, we must show that A plus quantity B plus C is equal to quantity A plus B plus C. Now, we know that the set of integers is only a subset of the set of real numbers denoted by capital R. So if that means that if A, B, C are integers and the set of integers is a subset of the set of real numbers, then A, B, C are real numbers. And we know from your algebra course that the set of real numbers satisfies the associative property, which means that in addition of real numbers, grouping is not important. That is, in addition of real numbers, the sum B plus C, the sum of A plus B plus C, because addition here is a binary operation, we can only combine two elements at a time. So if you choose to get first the sum, or if you choose to combine first B and C under the binary operation addition, and the result you add to the real number A, you will get the same result if you select to combine first the first two elements A and B by the operation addition, and the sum you combine with the third real number C, and the results are the same because addition of real numbers satisfies the associative property, which means that grouping is not important when you take the sum of real numbers or when you add real numbers. So we write the reasoning for this, that the set of integers satisfy the associative property. again, we say that because Z, the set of integers, is a subset, this notation indicates proper subset of the set of real numbers. Proper subset means that all the elements of Z, the set of integers, are also elements of the set R of real numbers. But there are elements in set R of real numbers that are not contained in set Z of integers. Therefore, Z is a proper subset of the set R of real numbers. And because Z is a proper subset of the set R of real numbers, we know that for any real numbers A, B, C element of R, the associative property is satisfied under addition. Therefore, we conclude that A plus quantity B plus C must be equal to quantity A plus B plus C. Now we verify the second property of a group, the existence of identity element. In your study of algebra, there is one of the properties of the set of real numbers under addition is the existence of identity element. In particular, we call this identity element under the binary operation addition, the additive identity, or the identity element for addition. And in the set of real numbers, under the binary operation addition, this identity element for addition or additive identity is the zero real number. This zero is an element of the set of real numbers R. But a zero is also element of the set of integers. And actually, the set containing only zero is one of the three subsets of the set of integers Z. So zero is an element of Z, the set of integers. And if you add 0 to any other element of the set C of integers, the sum would be any other element of set C. Because any other element of the set C of integers is also an element of R. And 0 has the property that if you add it to any other real number element of set R, the sum would be any other real number. We write now the second property satisfied by the set C of integers under the binary operation addition. And it is the existence of identity element. In this example, it is 0 under the operation addition. So we are sure that there is one element in the set of integers such that if you combine that element to any other element for every element of C, you combine it with 0. Using the binary operation addition, the sum is any other element A of the set of integers. and this must be true. 0 plus A is equal to A for every A element of C. If A is element of C, then A is a real number because C is a proper subset of R. That is, every integer is a real number. So if 0 is added to any other real number, the sum is that real number. And that's one of the properties of the set of real numbers. That is, there exists an identity element for addition in the set of real numbers, satisfying this property that if you add that identity element for addition, which is 0, to any other element or any other real number, the sum is the real number. So the second property of a group is satisfied by the set of integers under the binary operation addition. Now, another property of the set of real numbers under the binary operation addition is the existence of what we call additive inverse, or this additive inverse is also known as the negative of a real number. That is, for every real number, say A, there exists an additive inverse denoted by minus A. And minus A is also called the negative of A, or the additive inverse of A. And furthermore, if you combine A and its negative minus A by addition, that is A plus quantity minus A, the sum is equal to the additive identity or the identity element for addition, which is 0. Because as we have already shown that 0 is the identity element for the set of integers, if we take any other element, any other integer, positive or negative, and you take its negative, the answer is another integer element of the set C. Example, if you have the integer 7 and you take its negative, you get minus 7. And minus 7 is another element of the set of integers C. If you have minus 3 and you take its negative, negative of minus 3 is positive 3. Now, positive 3 is also in the set of integers Z. And positive 3 is the additive inverse or the negative of minus 3. Such that if you add minus 3 to its negative, which is positive 3, or if you add negative 3 to its additive inverse, positive 3, the sum is 0. And that is just a specific example. But that property is true for any integer element of C. For any integer you take from set C, there is a additive inverse for that any element of set C that is also contained in set C. And if you combine this element, any element of C, to its inverse or additive inverse or negative of that element of C, that additive inverse or negative of that element of C is also contained in C. And if you combine these two by addition, the sum is the identity element 0 that is contained in C. We represent this any element of C by A. we denote any arbitrary element of the set of integers z by a. So for every a element of c, there exists minus a element of c. As I said earlier, if a is 7, its additive inverse or negative is minus 7, and minus 7 is also an element of c. Or if a is equal to 3, negative 3, its additive inverse or negative is positive 3, and positive 3 is also element of c. And if you combine a to its negative minus a, the sum is equal to 0, which is the identity element for addition in set Z. Now, this minus a for this particular example of a group is called the additive inverse or negative of a. And they satisfy the property that the sum of a and its additive inverse or negative, the sum of a and its additive inverse or negative is equal to the identity element for addition under the binary operation addition defined in the set of integers z. We have shown that all the three properties of a group are satisfied by the set of integer z under the binary operation addition. Therefore, we conclude that z under addition is a group, and we write that as follows. We therefore conclude, because we have shown that the three properties G1, G2, and G3 of a group are satisfied by the set of integers under the operation addition, then set Z together with the binary operation addition is a group denoted by this notation, open parenthesis, the set, the non-empty set Z, comma, the binary operation addition, close parenthesis. The set Z together with the binary operation addition is a group. We now take another example. For our next example, consider the following problem. Determine if R is the set of real numbers under the binary operation star defined by a star b equals 2b minus a for any real numbers a, b, elements of R is a group. In this problem, the non-empty set is the set of real numbers R, and the binary operation star is defined by this formula or equation. This formula or equation tells us how to combine any two elements of R by the binary operation star. So this tells us that if you combine any two real numbers A and B by the binary operation star, the result is 2B minus A, twice the second real number minus the first real number in this notation. So we now verify if this set of real numbers together with this binary operation defined by this formula is a group. And again, to do that, you have to verify if all the three properties of a group are satisfied by the elements of R under this binary operation defined by this formula. And if at least one of these properties is not satisfied, then you conclude that R under this binary operation is not a group. And when you verify the properties, you always start with G sub 1, the first property, or the associativity or associative property. And to verify the associative property, we need three arbitrary elements from the set, the given non-empty set, in this example, the set of real numbers. And we denote the three arbitrary elements of R by A, B, C. We start with the first property of a group, the associative property. That is, we verify G1, and we need three arbitrary elements from the given non-empty set R, the set of real numbers, and we denote these three arbitrary elements by A, B, C. And to verify the first property of a group, the associative property or associativity, we show that A star quantity B star C is equal to quantity A star B star C. And we start calculating the value of the left-hand side using the binary operation star defined by this formula. We start from the left. Now, to combine A, B, C using the binary operation star, at the left-hand side, we first find the value of B star C using this binary operation defined by this formula. And this is now equal to A star the result when B and C are combined by the binary operation star. And the binary operation star is defined by this formula. That means if you combine A and B by the binary operation star, the result is twice the second real number minus the first real number. And this binary operation star applied to B star C will give us twice the second real number 2C minus the first real number B. Now we combine A, and this result when B and C are combined by the binary operation star. That is, we now get the value of A star quantity 2B minus C. A is the first real number, and this is a real number, the second real number. And by the binary operation star defined by this formula, A star quantity 2C minus B will give us twice 2 times the second real number minus the first real number A. We write 2 times the second real number 2C minus B. Minus the first real number A. And to simplify, we remove the grouping symbols by applying distributive property of multiplication over addition or subtraction. And this gives us 2 times 2c is 4c. 2 minus b, 2 times minus b is minus 2b. And the last term is minus a. Now we also compute the value of the right hand side of this equation, and we check if we compute this value at the right. We check if we would get the same value as the value of the left. If we get the same value for the right hand side, if we get the same value, 4c minus 2b minus a, then we conclude that associative property, this property associativity is satisfied by the set of real numbers under the operation star defined by this formula. So we write, on the other hand, we compute a quantity a star b star c. And at the right hand side, to get the value of a star b star c, we first group find the value of a star b. So we start finding the value of quantity a star b, and the result we combine with c under the same binary operation star. And using this definition of the binary operation star, a star b is equal to twice the second real number minus the first real number a. Hence, a star b is 2b minus a. And this result 2b minus a, that's now a single real number, we combine with the third real number c. And we apply again this formula that defines the binary operation star in R. This is now 2b minus a is your first real number and c is your second real number. And by this formula, quantity 2b minus a star c is equal to twice 2 times the second real number c. So that's 2c minus the first real number. Now 2b minus a star c is equal to 2 times the second real number minus the first real number. And because this has two terms, we write minus open parenthesis 2b minus a. Close parenthesis minus quantity 2b minus a. Again, we simplify by removing the grouping symbols, and we apply the left distributive property of multiplication over subtraction or addition. And this simplifies to, the first term is the same, 2c. Negative times 2b is minus 2b. Negative times minus a is plus a. Therefore, the value of quantity a star b star c is 2c minus 2b plus a. While the value of the left-hand side, a star quantities b star c is 4c minus 2b plus a. And we have shown that the value of the left is not equal to the value at the right. Therefore, the associativity property of a group is not satisfied by the set of real numbers under the binary operation star defined by this formula. And we conclude that the set R under this binary operation star defined by this formula is not a group. And there is no more need to verify G2, the second property, and G3, the third property of a group. Now, supposing the first property, G1, is satisfied, then you proceed and verify the second property, the existence of identity element in the given non-empty set. And if the second property is not satisfied, you conclude that the given non-empty set together with the given binary operation is not a group, and there is no more need to verify the third property of a group, G3. Now, supposing the first two properties of a group, G1 and G2, are satisfied, you proceed to verify the third property of a group, G3. And if the third property of a group, G3, is not satisfied, then you conclude that the given non-empty set together with the binary operation defined on that non-empty set is not a group. And here we write the conclusion. Our conclusion is that the set of real numbers are under this binary operation star defined by this formula is not a group. The set R together with this binary operation star is not a group. And our reason is that associativity or G1 is not satisfied. Because as we have shown, since A star quantity B star C is not equal to A quantity A star B star C. They have different values as we have shown. Therefore, the first property of a group is not satisfied, and we conclude that R under the binary operation star is not a group. For your practice, please try the following exercises. Number 1, let P be the set of non-zero rational real numbers, or simply rational numbers. Show that P together with the binary operation multiplication is a group. A rational number is a number of the form. A rational number is a number that is a ratio of two integers. These are examples of rational numbers A and B. A and B are real numbers. The ratio A over B is a rational number. A and B are integers, and the ratio of the integers A and B is a rational number. 3 over 7 is a rational number because it is a ratio of two integers, 3 and 7. 1 is an integer, 1 is a positive whole number, and it is a rational number because 1 can be written as the ratio of two integers that are the same and equal 2 and 2. And in number 1, you show that the set P of non-zero rational numbers under the operation multiplication is a group. It says P is a set of non-zero rational number. This means that 0 is a rational number because 0 can be written as the ratio. 0 can be written in many ways as the ratio of two integers, such as the integers 0 and 16. The ratio of 10 is, when you simplify this, is 0. 0 can also be written as the ratio of the integer 0 and the negative integer negative 6, but when this is simplified, it simplifies to 0. But these 0 rational numbers are not included in set P because number 1 says set P is the set of non-zero rational numbers. And number 2, determine if set Z, the set of integers, under the operation, the binary operation star defined by this formula, A star B equals A times B divided by 2. For every integers A and B, elements of Z is a group. In number 2, the binary operation star is defined by this formula. This formula gives you how to combine the integers A and B by the binary operation star. So to combine A and B by the binary operation star, multiply A, the first real number, by the first integer by the second integer B, and the product is divided by 2. For number 2, you start with verifying the associativity property, and if it is satisfied, you verify the second property. You must show in the second property of a group that there exists an identity element for cell C under this binary operation. And you cannot simply guess the identity element for the set of integers C under this binary operation star. You have to use the property of the identity element denoted by E when combined by any other element of C denoted by A. The result is the identity element E. And you also make use of the definition of the binary operation star given by this formula to find the identity, the value of E, the identity element, and see if its value, the value of E, is also in C. Because the second property of a group says that there is an identity element under the binary operation star in G, but this identity element is also in the non-empty set G. In number 2, the non-empty set G is C. And that concludes our discussion for today, and we will have some more examples of groups in the next lesson. And in addition to that, we will take the abelian group or commutative group. If all the three properties of a group are satisfied and the commutativity or commutative property is also satisfied by the elements of the non-empty set G under the given binary operation, then the group is called abelian or a billion group or commutative group. If you have questions about the lesson today, you ask your questions in the comments below. Thank you for joining me in my class today in Abstract Algebra.
I'm walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking.